Okay, we have an Alex problem here dealing with equilibrium here, and it gives us a certain chemical equation. And it is going to be methane is going to then come into equilibrium with C2H2 and H2. And it gives us an equilibrium constant right here. And I note right away that that's pretty small. Okay, and so what does a small equilibrium constant kind of mean to us? Well, let's go ahead and write the equilibrium equation first. Okay, and so that's going to be K sub P is going to equal the pressure of C2H2, and that is going to be raised to the first power right there. And it's going to be times the pressure of the H2, that is going to then be cubed. And this can be divided by the pressure of the CH4, that is going to be squared. And so a small equilibrium constant means that the numerator is quite small relative to the denominator, meaning that you have much more of the reactant than you do of the products. Okay, so that's what that means, is there's just not a lot of change. If you go back to your vessel here and you look in there and you'll see that most of that is still methane. Only a little bit has moved here to the right. Okay, so it gives us an initial amount of methane right here, and we'll assume then that there is no C2H2 or H2 in there. And so I can build my ice tables, and so I can start here and say that the initial, the change, the equilibrium, and what I like to do is just follow the equation, the chemical equation order. We got methane, we have C2H2, and finally we have the H2. Well, initially we have 8 atmospheres of the CH4, and we don't have any of the C2H2 or the H2. Okay, so I look at what the problem is asking. It's saying, can you find the equilibrium pressure of C2H2? Okay, so I'm going to set that as my x then, since that's what I'm trying to find. So that's going to change by x, and I look at my stoichiometry to get the others. Well, I know that C2H2 is going up, it has to, and so that's going to be plus x, so the H2 also has to go up, and so that is going to be plus up a 3x. Again, I get that stoichiometry right there. And then I have the methane, and I see that that is going to go down 2x. And so at equilibrium, I'm going to be 8 minus 2x, I'm going to be x, and I'm going to be 3x. Okay, well now, since I know my equilibrium, or I've set up my equilibrium concentrations, then, or pressures in this case, what I'm going to do is I'm going to rewrite this equation up here, rewrite that down here where I have some space. And so K sub P is equal to 2 times 10 to the negative 7th, and that's going to equal the equilibrium pressure C2H2, which we set as x, and that's going to be multiplied by 3x, the H2, that is going to then be cubed, and that's going to be divided by 8 minus 2x, which is going to be squared. Just taking these and I'm plugging them in to that equation that I see up here. Okay, and so that's what I have down here. Well, I can see that if I work this math right here, it's going to give me some really hairy math I really don't even want to deal with. Well, because K sub P is so low, that means that this change in x is going to be quite small, relatively speaking. And so anything where I add or subtract x, because x is so small, it's going to have almost no difference on the original amount. And so what I can do is I can just ignore any subtraction or addition of any of the terms that have x associated with it. Okay, so that will then allow me to sort of rewrite this, and so I'm going to say 2 times 10 to the negative 7th is going to equal, I'm just going to do this math up here, that's going to be, don't forget to cube that 3, that's going to give me 27 x to the 4th divided by, I've ignored that 2x term, and so that's going to give me 64. Okay, so now I can solve for this. I can take that 64 up there, multiply, and then take that 27 down there and divide. So just straight up algebra. I'm not going to go over how to do the algebra. But when I do that, I get this. I get 4.74 times 10 to the minus 7th is going to equal x to the 4th. Alright, I can do x to the 4th. I can put that into my calculator quite simply. And so when I do that, the 4th root, that's going to equal 0.0262. X equals, if I take that 4th root, of that, x equals 0.0262 atmospheres. Okay, it's asking for that with 1 sig fig. Okay, and so I'm going to say that's going to then equal 0.03 atmospheres. So this will be the answer that I will plug in. Okay, so these are doable. Actually, they're really doable. So what I do again, just to recap, is I write an equilibrium equation, set up my ice table properly. Because this value is so low, then what I can try to assume is that that I can ignore any addition or subtractions of the x's, which I did right in this area right here, do the math, and I come out here with atmospheres of 0.03. Now, it is important to check. We have a 5% rule that if this x value is indeed less than 5% of the original 8 atmospheres, then this is a pretty good assumption. So what I can do is I can take 0.03 divided by 8, and I can see that's going to be way less than 5%. You can actually do the calculation if you want. So this is a good assumption, and so I have finished the problem by calculating 0.03 atmospheres.